In this video, we're going to talk about volume and surface area in higher dimensions, and this is part 2 of 2 videos. Now, what we looked at last time in the first part was this table right here. Let me bring it up here. Okay, this table where it gives the volume and formulas for the volume and surface area of a ball of radius r in different dimensions. So notice, for example, in dimension 3 that the volume of a ball of radius r is 4/3 pi r cubed. Okay, and the surface area is 4 pi r squared. Now, if we're in dimension 2, the volume, well, what we really mean by volume is area in that case, but it would be pi r squared. And the surface area, and what we really mean is the circumference, is 2 pi r. Now, a couple things about this table that are we want to figure out is where do these formulas come from? Okay, we might notice some patterns within the formulas here, and if you look at this carefully enough, you'll see some nice patterns that arise. A couple other observations, though. Notice that the derivative of the formula for the volume of a ball in a certain dimension, say dimension 3 here, the derivative with respect to r gives you the surface area formula. So the derivative of 4/3 pi r cubed with respect to r gives you 4 pi r squared. And also in dimension 2, the derivative of pi r squared is just 2 pi r. Okay, so why is that the case? And that's actually the first thing we're going to start off in this video is talk about why is the derivative, the formula for the volume of a ball of radius r, why does that give you the surface area formula? Now, another thing that's interesting that we can look at is why is it in dimension 5 that the volume of the unit ball is the largest, right? So notice if r is 1 and our formula is for the volume of a ball of radius r, notice that in dimension 5 the volume is the largest. So what's going on with that? So in this video we're going to answer some of those questions. So in the last video we talked about the gamma function, we did a few integrals, and we're going to use those in this video. Okay, so let's go down and get started here. Okay, so notice that I'm using v sub n of r to denote the formula for the volume of a ball of radius r when we're in n-dimensional space, and s sub n of r is the surface area of that ball. And so the question is, why is the derivative of this formula for the volume give you the surface area of the formula? Okay, so suppose that we have no idea. Let's just try this in dimension 2 here. Suppose we have no idea what the formula is for the area of a circle. Okay, but we do know what the formula is for the circumference. So we don't know that the area is pi r squared, but we do know the circumference is 2 pi r. How could we use the circumference formula to find the area formula? Okay, so notice that in Desmos here, I've drawn a circle of, we'll call it radius r. So a circle centered at the origin has a radius of r. So the question though is, how can we find the formula for the area of this circle if we know the formula for the circumference of the circle? Okay, so what we're going to do is take this circle and divide it up into a bunch of annuli. Okay, so what we're going to do is take this interval from 0 out to r and chop it up into a bunch of sub-intervals, right? So we'll assume these sub-intervals have equal length here. So I think I have 15 sub-intervals that I've drawn. So I have really 15 annuli that I've drawn here. And notice we could find the area of this circle by finding the area, first of all, of this outer annulus here, okay, the area between these two curves here, and then find the area of this annulus, okay, and then find the area of inside this annulus, and add up all those areas, and if we add up the areas of all those annuli, that will equal the area of the circle. Notice this is similar to when we're talking about finding the area under a curve using Riemann sums, right? We chop this interval, in this case it's 0 to 5, up into a whole bunch of sub-intervals, and we draw rectangles above those intervals based on the height of the function. And adding up the areas of those rectangles gives you an approximation of the area underneath the curve. Okay, so let's go back to our picture here. The question we can ask, though, is what is the area of one of these annuluses, or annuli? Okay, and what we can do is this. Okay, notice that I've redrawn the circle here, and I've just drawn one annulus, and a question that we could ask is what is the area inside this annulus here? Okay, and again, suppose we don't know the formula for the area of a circle. Okay, well, one way that we could approximate the area of this annulus would be to take the thickness of this annulus, which I'm going to call delta x. And by the way, I've labeled the endpoints here of these subintervals, x0, x1, x2, x3, all the way up to x sub n. So x sub n is really just r, and x sub 0 is 0. And we're looking at the kth subinterval here, and I've labeled the widths of each of these intervals delta x. One way that we could approximate the area of this annulus is to take the thickness of the annulus, which is delta x, and multiply it by the circumference of the annulus, and that would give us the area. Now, what do I mean by circumference? Well, do we mean like the inside circumference here, or the outside circumference, or something in between? Well, I've picked a point in here. I call it xk star. We're in the kth subinterval. I picked a point called xk star, and so I guess we could look at the circle that has that radius at xk star there. Now again, that will not give us the exact area of this annulus, but it will be a good enough approximation if the thickness is not very much, if it's a thin annulus. In fact, the thinner the annulus, the less it really matters which point you pick. And the idea is we're going to take the limit as the number of these annuli go to infinity, so as their thickness goes to 0, so it really won't matter which point we pick if in the limit. Okay, so again, we can imagine the area of this annulus being the thickness of the annulus, this width here, multiplied by the circumference. And again, by circumference, that's where we have to just pick a point in here and take the circumference there. Again, ultimately, we're going to take the limit. So this is really just be an approximation of the area of this annulus. Okay, let's go back to our PDF. Right here, and so I said consider the picture and divide that interval from 0 to r into n equals subintervals, and we labeled these endpoints x0 up to xn, and we formed an annulus using each subinterval, and notice that the area of the circle will be equal to the sum of the areas of those annuli. Okay, and within the kth subinterval, choose a point xk star, so within each subinterval. In the picture, I've done this for the 11th subinterval, so if you count it out, that was the 11th one that we looked at. And if the annuli are thin enough, then the area of the annulus will be approximately equal to the thickness of the annulus, which we'll call delta x, multiplied by its circumference. So that is the area of the kth annulus will be approximately 2 pi xk star, okay, 2 pi r, but the r was xk star, times delta x. Okay, so again, let's go back to our picture here. Okay, notice that the area is going to be the circumference, which is 2 pi times the radius, but the radius is this xk star, times the thickness, which is delta x. And by the way, we can come back here and look at this picture. Notice that if we just find the sum of the areas of all these annuli, that'll give us the area of the circle. Okay, so we do that for each of those n subintervals. We find this point in the kth subinterval, we find xk star. So in the first interval, we'll find x sub 1 star. So the area of the inside annulus will be 2 pi x sub 1 star times delta x. The area of the next one will be 2 pi x sub 2 star times delta x, and so on. And the last one, that outer ring, that outer annulus, will have area 2 pi x n star times delta x, or it'll be approximately equal to this. Because, again, we're having to pick our circumference kind of arbitrarily within each interval. Okay, but notice we could write this in summation notation as 2 pi xk star times delta x, where k runs from 1 to n. Okay, but notice this is only an approximation. To get the exact area of the circle, we need to take the limit of this expression as n goes to infinity, right? As the number of those annuli go to infinity. So, right, so as they get thinner and thinner and thinner, but the number of them goes to infinity, that will give us the area of the circle. The area of the circle is just the limit as n goes to infinity of this. But what's the limit as n goes to infinity of this? Well, this is really just a Riemann sum, a limit of a Riemann sum, so it's an integral, right? The limit of the sum here turns into this integral symbol, and we're integrating from 0 to r. The 2 pi xk star becomes 2 pi x, and the delta x becomes dx. This is really just the definition of definite integral. Okay, that's what we're using here. So notice we can find the area of our circle by doing this integral. Now let's actually calculate the integral. Let's see what happens. So what is the integral from 0 to r of 2 pi x dx? Well, the integral of 2 pi x is going to be 2 pi x squared over 2. The 2's will divide out, and we just get pi x squared evaluated from 0 to r. If we plug in r for x and then plug in 0 for x and subtract, we just get pi r squared. And notice we found the formula for the area of a circle, right? We found it by using the formula for the area of, or for the circumference, right? So what we looked at to find the area of the annulus, we multiplied the circumference times the thickness. Okay, so notice ultimately it just came from doing an integral of the formula for the circumference, right? We have 2 pi x, it was really x k star, times delta x, which was the thickness, but it turned into this integral. So we're just integrating the circumference formula to get the area formula. Okay, now, by the way, you can do the exact same thing if you're in dimension 3. So a similar thing happens when we consider a sphere in 3-dimensional case. In that case, though, instead of dividing the sphere into annuli, we divide it into shells. And a good way to think about this is to think about peeling an onion. So let me draw, I have a picture here of an onion. Okay, notice one way to find the total volume of this onion would be to find the volume of each of the layers of the onion. Right, so what's the volume of this layer of the onion? Okay, what's the volume of this layer of the onion? We're not talking about area anymore, we're talking about volume of that layer. Okay, and how do we find the volume of this layer? Well, if we know the formula for the surface area of a sphere, we can take that formula and multiply it by the thickness of this, and that will give us an approximation of the area, or I'm sorry, the volume of that shell. And we take the sum of all those volumes and we take the limit of the sums, the limit as the number of those layers goes to infinity, and so the thickness goes to 0, and it turns into an integral again. And again, you get the same idea as in 2-dimensional space, that we can find the volume of the onion by finding the volumes of all the layers of the onion, adding them up. And we can approximate the volume of each layer of the onion by multiplying the thickness of the layer by the surface area of the layer. Okay, and working out the details, I'm not going to do it in this video, but it's not hard to show that the formula for the volume of the sphere is really just the integral of the formula for the surface area. Okay, in fact, this reasoning works in all dimensions. Okay, and in fact, that really explains why the derivative of the volume formula gives you the surface area formula. Well, ultimately what we showed was that the integral of the surface area formula gives you the volume formula, but just the reverse of that would just say that the derivative of the volume gives you the surface area. Okay, so that's why we had this mysterious issue way back up here in this this mysterious thing happening where the derivative of these formulas were always giving us these. Okay, now I still haven't explained where these formulas come from. And again, you'll notice some patterns. Something that might seem a little bit strange though is what about these coefficients? Where are these coefficients coming from? Okay, so let's talk about where do these formulas in this video come from. Okay, now first thing I want to think about is consider two circles centered at the origin. One of them that has radius 1 and the other that has radius 5. How do their areas compare? Okay, so we have two circles. One of them has a radius that's 5 times as large as the other. How do their areas compare? So notice in Desmos here, I do have a circle of radius 1 here, centered at the origin, and a circle of radius 5. So this circle, you might say it's 5 times as big, but what we really mean is the radius is 5 times as big. In fact, in terms of area, notice this circle is way more than 5 times the area of this one. In fact, if you think of the area of this one, you could easily put one of those like right there, put another one right there, another one there, another one there, and you could easily fit 5 in here with tons of room left over. In fact, the area of this circle is actually 25 times the area of this one, right? If you think of pi r squared, right, this would be 25 pi, and this would have an area of 1 pi, right? So this area is 25 times as big. So notice that if you multiply the radius by 5, the area multiplies by 25. If we multiply the radius by 7, the area would go up by 49. Or if you multiply the radius by 10, the area would go up by 100, right? It always goes up by the square of whatever the ratio is between the radii. Okay, and actually in 3-dimensional space, if we talked about spheres, okay, let's come back to our PDF here. So notice that the bigger circle has 5 squared equals 25 times the area. By the way, the circumference is only 5 times as large. Okay, so if we go back to this picture right here, the circumference here is not 25 times the circumference of this, it's only 5 times as much. Okay, so it goes up in a linear fashion for the circumference, whereas the area goes up in a quadratic fashion. Okay, so now similarly, a sphere in 3 space that has a radius 5 times as large as the radius of another sphere will have a volume that's 125 times as large. So in other words, if you make the radius 5 times as big, the volume goes up by 125 times as much. It goes up by a factor of a cube. And likewise, if you made the radius 10 times as large, let's say the volume would be 1,000 times as big, 10 cubed, right? It goes up by a cubic factor. Now the surface area goes up by a square factor, right? So if you make the radius 5 times as large, the surface area will be 25 times as large when we're talking about a sphere in 3 space. Okay, so basically I'm talking about a scaling argument here. So I've basically used a scaling type argument. You can think about this for a little bit to see if this makes sense. But a scaling argument shows that the volume of a ball of radius r in n-dimensional space has to be some constant k times r to the n. Okay, where r is the radius, where the surface area, it has to be some constant times r to the n minus 1. Okay, for some constants, k and m. Okay, that's what this scaling argument shows. Well, finally, notice that plugging in r equals 1, what's v sub n of 1? Well, wouldn't that just be k? Okay, if you plugged in 1 for r, and s sub n of 1 would just be m. Okay, so notice we can rewrite v sub n of r equals k times r to the n as v sub n of r equals v sub n of 1 times r to the n. So in other words, the volume of a ball of radius r in n-dimensional space is the same as the volume of a ball of radius 1, the volume of a unit ball in n-dimensional space, times r to the n. And same thing with the surface area. The surface area of a ball of radius r in n-dimensional space will be the surface area of the unit ball, okay, the ball of radius 1, times r to the n minus 1. Okay, so really our big question, if we're trying to find v sub n of r and s sub n of r, okay, that will give us those formulas in the original table that we looked at. What we really need to do is find v sub n of 1, volume of the unit ball in n-dimensional space, and s sub n of 1. Now, it turns out, though, that once you have one of these formulas, once you have v sub n of r, you can find s sub n of r just by taking a derivative. Or likewise, if you have s sub n of r, you can find v sub n of r just by doing an integral, right, an antiderivative. So really, we just need to find either v sub n of 1 or s sub n of 1, and that will give us all the formulas in the table that we have. Now, it turns out it's easier to find s sub n of 1, surface area of a ball of radius 1, than the volume of a ball. Okay, so how do we find the surface area of a ball of radius 1 in n-dimensional space? Well, we're going to do it in a kind of a strange way. We're going to compute a certain integral here that looks like, you know, what does this integral have to do with anything here? But we're going to compute this integral that we'll call an auxiliary integral. Okay, and this is really an integral over n space. Okay, we're integrating from negative infinity to infinity of the integral from negative infinity to infinity, and so on. And we're doing this with n variables here. So instead of just like a xy or an xy and z, we're imagining we have n variables. And the function we're integrating is e to the negative, the quantity x1 squared plus x2 squared, and so on, plus xn squared. Okay, how do we calculate this integral? Okay, well, one way to do it is essentially to just break it up. We can recognize this function is really just e to the negative x1 squared times e to the negative x2 squared times, and so on, and finally times e to the negative xn squared. And then we can just split up this integral into really a product of n integrals, and all those n integrals are ultimately the same. In fact, they all have this form, integral from negative infinity to infinity of e to the negative x squared dx. So we really just have this integral raised to the nth power. Well, this is the exact integral that we did in the last video. Okay, in the last video, we found the value of this integral to be the square root of pi. So the value of this n dimensional integral here, integral over n dimensional space, actually equals the square root of pi raised to the n power, or pi to the n over 2, right? The square root of pi is just pi to the 1/2 power. So pi to the 1/2 to the n is really pi to the 1/2 n. So that's this. Okay, so the point is, one way of calculating this integral gives us that it's pi to the n over 2. Okay, in fact, that's just the answer. The value of this integral is pi to the n over 2. But we're going to look at another way of evaluating that integral. So another way to compute the integral is to think of the whole of n-dimensional space as being made up of shells centered at the origin. Okay, in this way we can use the spherical symmetry of this function here to compute the integral as using a kind of polar coordinates in higher dimensions. So this function is really spherically symmetric, right? It's symmetric with respect to the origin, in the sense that suppose you're on a sphere of radius 5. Okay, centered at the origin. Well, what that means is that x1 squared plus x2 squared all the way up to plus xn squared would equal 25. Okay, so if x1 squared plus x2 squared plus all the way up to xn squared equals 25, well, there's lots of different ordered n tuples, x1, x2, all the way up to xn, where that's the case. That would add up to 25. All of those n tuples, though, would lie along a sphere. Well, this function on all of those n tuples, all those points on that sphere, would have a value of e to the negative 25th power. Okay, so on the sphere of radius 5, centered at the origin, this function here has a value of e to the negative 25th at every point in that sphere, right? It's symmetric with respect to the origin. So it turns out we can think of this as really a one-dimensional integral where we're integrating from 0 to infinity of e to the negative r squared, okay, where r is the radius of that sphere. But then we have to multiply it by the formula for the surface area of a ball of radius r. Okay, and this is maybe the trickiest step to kind of get in this whole video here. But I want you to think about, so I'm not really going to go into try to explain it, but just think about why is this integral equal to this, and why does this s sub n of r pop up here? Okay, so maybe it's easiest to think about, instead of having n variables, suppose you just have 2, and so you just have, instead of x1, x2 up to xn, suppose you just have xy, so dx, dy, and you have e to the negative x squared plus y squared. Okay, why does it have this s sub n of r? So if you can maybe visualize that one a little bit better. Okay, but let's suppose that's the case. You've figured that out. Well, s sub n of r, we just showed it's equal to s sub n of 1, the surface area of a ball of radius 1, times r to the n minus 1. Now notice this s sub n of 1 doesn't have any r's in it, so we can pull it out in front of the integral. It's constant with respect to this integral here. So we have s sub n of r, or s sub n of 1 times this integral. Okay, so notice equating our answers. One way of calculating this crazy integral here, we got that it was pi to the n over 2. Okay, another way of calculating that same integral, we got that it's this. So pi to the n over 2 should equal this, right? Pi to the n over 2 equals s sub n of 1 times this integral. Now remember, we're trying to find what's s sub n of 1, right? So the way we can find s sub n of 1 is it's going to be this, okay, pi to the n over 2 divided by the value of this integral. Okay, so the question is, what's the value of this integral? Once we have the value of this integral, we'll have s sub n of 1, because s sub n of 1 will be this divided by this. Okay, so what is this integral? Well, the integral from 0 to infinity of e to the negative r squared times r to the n minus 1 dr is equal to this. Well, here I've just done a u substitution. I've let u be r squared. So notice we have e to the negative r squared. It'd be e to the negative u. Now, dr is not equal to du. In fact, du is equal to 2r dr. That's why the 1/2 happens in here. But also, r is equal to the square root of u is another way to think about this. But notice that r being the square root of u, we'd have r to the n minus 1 would be the same thing as the square root of u to the n minus 1. Or in other words, u to the 1/2 to the n minus 1. But that would give us u to the n over 2 minus 1/2. But notice the fact that we have this here, that the r is the square root of u, makes this being a minus 1 instead of a minus 1/2, because we also have this r, 2r dr that's equal to du. So anyways, you can go through this details here. It's hard to explain it in words here, but go through the details doing this u substitution. You'll see that this equals this. Okay, you might want to write it out or something. Okay, well, of course, you can pull the 1/2 out in front of the integral now. And notice, though, what is this integral here? Well, this integral is just the gamma function where we're using n over 2 for our input. Now, with the gamma function, I think I used a t. No, I think I used an x. The gamma function, gamma of x, was the integral, or gamma of n, I'm sorry, was the integral from 0 to infinity of e to the negative x times x to the n minus 1 dx. In fact, let's go back up and find that up here, right? Our gamma function, we defined it like this. Gamma of n is the integral from 0 to infinity of x to the n minus 1 times e to the minus x dx. Right, so that's gamma of n. Now, gamma of n over 2 would be this with n over 2. Now, our integral that we were looking at was using a u instead of an x. Okay? So, let's come back down to our integral again. And so notice what we have is that this integral is just equal to gamma of n over 2, and we still have the 1/2 out front. Okay, so the point is that this is 1/2 times gamma of n over 2. So s sub n of 1 is pi to the n over 2 divided by that. Okay, so I've just rewritten this. S sub n of 1 is now dividing by 1/2. It's like multiplying by 2. So we really had a 1/2 on the bottom, but it can become a 2 on the top. 2 pi to the n over 2 over gamma of n over 2. Okay, that's S sub n of 1. So notice we found our formula for S sub n of 1, and now we have S sub n of r is just that S sub n of 1 times r to the n minus 1. Okay, so that's what we have. There's our formula for S sub n of r. That's what we've been looking for. And now if we just integrate with respect to r, so notice all of these are constants here with respect to r anyway, except for the r to the n minus 1. So integrating this with respect to r just means we raise this power up. And so instead of r to the n minus 1, it becomes r to the n. And then we divide by n. So this formula down here is the same as this, only we have an n there instead of n minus 1, and we have an n down there. Okay, so that's the formula for the volume and surface area. And notice they both involve the gamma function. It's kind of strange. Now, let's actually check this here to see if this actually works. So let's look at V sub 3 of r. So let's look at this formula when n is 3. Okay, so the volume of a ball of radius r in three-dimensional space should be 4/3 pi r cubed. But if we plug in 3 for n, what happens? Well, we get 2 times pi to the 3/2 times r cubed. That's what we have, 2 pi to the 3/2 times r cubed, over 3 times gamma of 3/2. Now remember, gamma of 3/2, we figured out gamma of 1/2 and gamma of 3/2 and gamma of 5/2 last time. In fact, gamma of 3/2 was 1/2 times gamma of 1/2, but gamma of 1/2 was pi to the 1/2 power, the square root of pi. So notice what we end up getting. This 1/2 down there can become a 2 on the top, and we have 2 times 2/3, that's 4/3. We have gamma to the 3/2 divided by gamma to the pi to the 3/2 divided by pi to the 1/2. That's just pi. Okay, so notice the strange thing here in this formula. So we get our formula here, 4/3 pi r cubed. Notice the strange thing. You might think it's weird. Why do we have these fractional powers of pi up here? Like if n is odd. If n is odd, if n is 7, we have pi to the 7/2. Or if n is 9, we have pi to the 9/2. Well, notice none of the original formulas had like pi to a fractional power. What happens? Well, the gamma function, when you're taking gamma of 7/2 or gamma of 9/2, it ultimately ends up being some constant times the square root of pi. So those cancel out, and you end up just having pi to the 1 or pi to the 2 or pi to the 3, pi to some whole number power. Okay, so the formula really works. So that's ultimately where the formulas in this table come from. Okay, so now let's continue on here and answer our last question here. Strangely, note that the formulas, before we answer the last question, note that these formulas, S sub n of r and V sub n of r, make sense even if n is not an integer. Now remember, n was our dimension. You think of like 2-dimensional space or 3-dimensional space or 4-dimensional space. Could you think of like a fractional dimensional space? Does that even kind of make sense? Or what does a ball look like in a fractional dimensional space? Well, it's kind of strange that these formulas for V sub n of r and S sub n of r even work if n is not a whole number, right? You can take gamma of like 7.5 over 2 or 7.38 divided by 2. And you can take pi to the 7.38 over 2 power. And so you actually have formulas for the volume of a ball of radius r, or the surface area of a ball of radius r in n-dimensional space, even if n is not an integer. Now, the crazy thing is it doesn't even make sense to talk about a ball in a fractional dimensional space. Okay, but these formulas would still work, and it's kind of strange. But by the way, it also might seem bizarre that in dimension 5, the volume of the unit ball is largest. Okay, so if we go up in this table here, notice that in dimension 5, the volume of the unit ball maxes out. But it turns out this is a little bit illusory because in some sense we're not really comparing apples to apples. We're comparing apples to oranges. Because if we were to measure this in, say, centimeters or inches, well, in dimension 3, our volume would have inches cubed or centimeters cubed, whereas in dimension 2, it would be square inches or square centimeters. Dimension 4 would be centimeters to the 4th power, inches to the 4th power. So we're not really comparing apples to oranges. So what we'd really need to do to be comparing apples to apples is in dimension 2 to take not just the volume of the unit ball, but the square root of that volume, so that our inches squared becomes inches. And then in dimension 3, we take the cube root of this number. And then in dimension 4, take the 4th root of this number. And if you do that, okay, I haven't written it down, it turns out these numbers always go down. So it actually doesn't max out in dimension 5. The values of these things always go down. Okay, so we don't get this strange peak at 5. Okay, so let's come back to here. So the volumes of the balls in different dimensions are not comparable. For example, the volume of a ball in dimension 2 may be measured in square meters, but in dimension 3, it's cubic meters are used. So the correct quantity to compare in different dimensions is not the volume, but the nth root of the volume. Now, one final question we could ask is when we do compare these apples to apples, the volume of the unit ball decreases as n increases. Now, why is that? Okay, well, let's look first of all in dimension 2. Okay, if we're in dimension 2, one of the questions we could ask is what percentage of this square here does the unit ball take up? Now, this square really has a length on each side of 2. The radius of this circle is 1 here. Okay, so we're looking at the unit ball or the unit circle. And so what percentage of this square does the circle take up? It looks like it's maybe like 3/4 of it or 80%, something like that. Well, we can actually figure it out exactly. Notice the area of this square is going to be 2 times 2. It's going to be 4. Whereas the area of this circle is pi r squared, but the r is 1, so it's just pi, right? The area of this circle is pi. The area of this square is 4. So the percentage of the square that the circle takes up is pi over 4. Now, 3/4, it would be 75%, right? 0.75. Pi over 4 is a little bit bigger than that. In fact, I figured out it's about 78.5%. So 78%, 79%, something like that. That's pi over 4. That's the percentage of the square that this circle takes up. Now, what if we kind of bump up the dimension a little bit, and we're not going to look at a sphere here. We're going to bump this up and look at a cylinder here inside of a box, and I've drawn this the best I can. So I made this drawing right here. So notice at the bottom here we really have like a unit circle here, and we also have the square that it's inside, but I bumped it up a dimension. I'm not looking at a sphere here, I'm looking at a cylinder. Okay, so this cylinder lies inside this box, and a question we could ask is what percentage of the box does this cylinder take up? Well, notice, shouldn't it be the exact same percentage that this circle takes up of this square? In fact, the percentage of the box that this takes up should also be 78.5% or pi over 4, right? If you just think about it for a second, it makes total sense, right? So notice the percentage of the box that this cylinder takes up is about 78.5%. But notice if we put a sphere inside here, let's put a sphere centered right at the center of this box here and make the radius be 1. Okay, notice wouldn't that sphere lie inside this cylinder? Okay, in fact, let me find a picture here. That sphere would lie inside this. In fact, notice here, here's a cylinder right here, and there's a sphere. Notice that the sphere lies entirely inside that cylinder. So the sphere has a radius of 1, and the cylinder has a radius of 1. Now the cylinder has a height of 2 here, but the sphere lies entirely inside that cylinder. So the sphere has a smaller volume than the volume of that cylinder, right? So the point is the sphere should take up a smaller percentage of the box than that circle did of the square, because the circle takes up the same percentage of the square that this cylinder takes up of the box, but this sphere lies inside the cylinder, so the sphere takes up a smaller percentage of the box than the cylinder did. Okay, so notice we bumped it up a dimension, and this sphere in 3-dimensional space takes up a smaller percentage of that box. Now the box would have the same center as the center of the sphere, and the sides of the box would be 2. Okay, that takes up a smaller percentage of the box than this initial, and see if I can find it again, this initial circle took up of the square. Okay, so in dimension 2, this percentage was bigger than when we were in dimension 3. So notice the volume of the unit ball is in some sense getting smaller. That kind of helps explain why when we compare apples to apples, the volume of the unit ball actually gets smaller. Okay, well that's all. I know there's a few steps I went a little quickly by but I think if you stop the video at different points, hopefully you should be able to understand all the details.